Today, we explore one of the most provocative questions in modern physics. We follow gravity from its earliest description as a force that pulls bodies together to Einstein's realization that it is the very shape of space-time guiding matter along curved paths. Then we step into stranger territory, where black holes glow with temperature, horizons store information, and space-time behaves like a thermodynamic system. We investigate whether the order we see in the cosmos might rise from the statistical tendencies of unseen microscopic ingredients, the way heat or pressure emerges from countless particles we never observe directly. Along the way, we examine Jacobson's idea that Einstein's equations can arise from entropy, Verlinde's attempt to rebuild gravity from information itself, and the holographic principle that suggests everything within a region of space may be encoded on a distant boundary. We walk carefully, separating what is known from what is only suspected, weighing each hypothesis against the evidence. In the final steps, we move toward the frontier, where quantum gravity, cosmological observations, and information theory converge, searching for the hidden structure that might give birth to spacetime. And with these questions echoing softly in our minds, we turn toward the cosmos. Let us jump straight into the universe. For as long as humans have watched objects fall, watched planets drift across the night sky, and felt the steady pull that anchors every gesture we make, gravity has seemed like an unquestionable presence, a quiet rhythm guiding the world without ever revealing its source. Yet when we begin tracing the long path of ideas that led from ancient observations to the physics of today, we find that gravity has always been a mystery, wearing a familiar face. Newton described it with extraordinary precision, but he did not explain what it was. Einstein reshaped it into the curvature of space-time, but even that profound leap did not unveil its ultimate origin. And as we move deeper into the modern landscape where quantum theory and relativity stand side by side yet refuse to merge, gravity begins to look less like a settled explanation and more like a question waiting patiently at the foundation of the universe. Imagine the world as Newton saw it. Celestial motions followed patterns so exact that entire planetary orbits could be predicted centuries into the future, and the fall of an apple could be tied to the movement of the moon. Newton wrote gravity as a mathematical rule that allowed nature to speak with clarity, yet he never claimed to know what mechanism lay behind the attraction. He avoided speculation, leaving the cause unspoken. To him, the force was a fact, as real as the planets themselves, a universal link between all masses. But a rule is not an origin, and even in its brilliance, Newton's framework offered no microscopic story, no picture of how matter could reach across emptiness to pull other matter towards it. Centuries passed, and with them came Einstein, whose insight altered the meaning of gravity in ways few could have imagined. Instead of treating gravity as a force acting at a distance, he described space-time as a fabric capable of bending and curving. Massive bodies deform this fabric, and smaller bodies follow its contours, moving along what appear to be curved trajectories. Einstein's equations link the content of the universe to the geometry that surrounds it, and for the first time, gravity became not a messenger between objects, but a property of space itself. Experimental confirmations arrived one after another. The bending of starlight during eclipses, the precision with which Mercury's orbit precesses, the slowing of clocks in stronger gravitational fields, and more recently, the direct detection of gravitational waves, all revealed a consistent picture that has endured for more than a century. And yet, for all its success, the theory remains incomplete. It merges poorly with quantum field theory, which describes every other known interaction. When Einstein's equations are pushed into extreme environments, such as the centers of black holes or the earliest moments after the Big Bang, they predict singularities where physical quantities explode in ways that cannot make sense. Information puzzles arise, hinting that something deeper must lurk beneath the smooth geometry we observe. The more closely scientists examine the fabric of spacetime, the more it begins to resemble the surface of an ocean. From far away, the water looks continuous, but up close it is made of countless molecules behaving in ways that generate the waves we see. Perhaps spacetime too is woven from unseen constituents, and gravity is not a fundamental commandment of nature, but an emergent tendency of something more microscopic. In physics, emergence has a long history of producing behaviors far grander than their ingredients. Consider how temperature emerges from trillions of particles moving chaotically, or how pressure arises from collisions that no single molecule could express alone. Superconductivity, superfluidity, and magnetism all manifest from collective rules that have no meaning when applied to an isolated particle. These examples remind us that not every law of nature must be fundamental. Some laws rise from deeper layers, becoming universal only because enormous numbers of microscopic events average themselves into clarity. If gravity belongs to this category, then its familiar form might be the large-scale expression of countless informational or statistical effects that have yet to be understood. This idea is not presented as truth, but as possibility. Scientists explore it because gravity continues to evade a complete and unified description. Some imagine that the universe contains far more degrees of freedom than we currently observe, perhaps hidden within quantum fields or entanglement structures that encode geometry itself. Others speculate that gravity might be a thermodynamic phenomenon, an expression of entropy guiding systems towards states with larger numbers of microscopic configurations. In such a picture, the attraction between masses could resemble the behavior of stretch polymers or the diffusion of particles, not through any mechanical pull, but through the statistical preference of nature for more probable arrangements. If this line of thinking holds even a grain of truth, it could reshape our understanding of space-time, energy, and the fundamental architecture of the cosmos. But before we can follow these ideas further, we must first ground ourselves in the concepts that will guide the journey. To ask whether gravity could be an emergent, entropic phenomenon, we must understand entropy with care. It is a word too easily misunderstood, often mistaken for chaos or disorder, when in physics it is something far more precise, far more revealing. The story of gravity cannot be separated from the story of information, and the next step requires us to confront that connection directly. The effort to understand gravity more deeply begins by stepping back to consider what a physical explanation truly demands. When scientists search for the origin of a phenomenon, they do not ask only how it behaves, but why its behavior arises from more elementary ingredients. For electricity and magnetism, this reduction leads to charged particles and the exchange of photons. For the strong and weak nuclear interactions, it leads to quantum fields and symmetries whose properties have been probed in accelerators. But for gravity, the trail grows faint. Einstein's equation describes how space-time curves in response to energy, but it does not reveal what space-time is made of. It presents geometry as something smooth and continuous, even though quantum mechanics insists that nature at the smallest scales should be granular, fluctuating, and probabilistic. The tension between these views creates a gap that has refused to close, suggesting that space-time might not be fundamental after all. To explore this possibility, imagine shrinking your perspective down to unimaginable smallness, far beyond any scale we can currently observe. At such depths, the familiar smoothness of geometry may disappear, replaced by some hidden structure whose collective behavior produces what we call space-time. The notion is unsettling, yet physics has encountered similar surprises before. Sound waves behave as if they are independent entities, though they are simply coordinated movements of atoms. Fluids flow as if they were continuous, yet every drop is a swarm of molecules whose interactions are so numerous that the collective picture becomes simpler than the microscopic truth. In this light, gravity's elegance might be a sign not of simplicity, but of averaging, the same way that temperature glosses over the frantic dance of molecules to produce a single measurable quantity. This perspective becomes even more compelling when we examine where general relativity begins to strain. In regions of extreme curvature, such as those near black hole interiors, the theory predicts impossibilities. Quantities that should remain finite instead diverge toward infinity, a signal that the mathematical framework cannot survive in those conditions. Inflationary models of the early universe also hint at limits, where the smoothness of spacetime near the Big Bang seems to conceal a more chaotic, quantum-dominated landscape. These tensions do not diminish Einstein's achievement, but instead highlight the incompleteness that inevitably arises when a theory describes nature beautifully at one scale, yet remains silent about its foundation at another. Modern physics attempts to bridge this gap with quantum field theory, which excels at describing particles and forces in flat or gently curved spacetime. But gravity refuses to fit comfortably within this framework. The naive attempt to quantize spacetime in the same way we quantize electromagnetic fields results in uncontrollable infinities. Renormalization techniques that rescue other interactions fail here, pointing once again to the possibility that we are trying to quantize the wrong thing. If spacetime is emergent, then quantizing it directly may be as misguided as attempting to quantize a wave in the ocean by treating the ocean itself as a fundamental field. The wave is real, but it is not basic. It is a behavior, a collective expression, not an ingredient. Gravity might share this distinction. Yet even as these cracks appear, general relativity continues to withstand experimental scrutiny. Gravitational waves ripple across the cosmos exactly as predicted. Clocks aboard satellites tick at rates that reflect the curvature of spacetime with exquisite precision. Even the bending of light around massive galaxies matches the equations to astonishing accuracy. This duality, where a theory can be both incomplete and astonishingly accurate, is nothing new in science. Newtonian mechanics remained indispensable long after relativity replaced it at a deeper level. In the same way, general relativity may be a broad but approximate description of a phenomenon rooted in microphysics that we have not yet uncovered. To move closer to this hidden layer, researchers study patterns that hint at thermodynamic behavior within spacetime. Certain principles, once believed to belong only to heat and disorder, now appear in gravitational settings as well. Black holes possess temperatures and entropies. Horizons hide information in ways that resemble thermodynamic systems. Even the simple act of accelerating through empty space produces a temperature, suggesting that vacuum and horizon properties are intimately tied to the number of microscopic configurations nature allows. These clues do not prove that gravity itself is entropic, but they suggest a relationship between geometry and information that is too persistent to ignore. This growing network of ideas raises a compelling possibility. What if mass and energy curve spacetime, not because of some geometric commandment, but because spacetime naturally organizes itself into configurations that maximize entropy under certain conditions? In this view, the curvature we observe might be the large-scale result of microscopic preferences, a statistical balancing act occurring behind the scenes. It would mean that the familiar attraction between masses could be the echo of a deeper push towards states that contain more ways for nature to arrange its unseen degrees of freedom. The laws of gravity, elegant and precise as they are, might then be the thermodynamic signature of this hidden tendency. But this is only the beginning of the inquiry. To follow the thread further, we must turn toward the concept that lies at the center of all thermodynamic reasoning, the idea that tells us how systems evolve and why. Before any claim about entropic gravity can be tested or even framed properly, we must first understand entropy with clarity, without metaphor, without vague notions of disorder. Entropy is a language, one that counts possibilities rather than particles, and it will shape every step of what comes next. To appreciate why entropy may hold the key to gravity's deeper nature, we must reflect on how profoundly the concept has shaped our understanding of physical systems. Entropy is not a substance and not a measure of disorder in the casual sense. It is a way of counting how many microscopic arrangements correspond to what we observe on larger scales. Whenever a system seems to follow a preferred direction, drifting from one state to another in a way that appears almost purposeful, it is entropy guiding the motion. This guiding is not intentional. It is statistical inevitability. More microstates simply exist on one side of a boundary than on the other, and the system flows in that direction the way a river flows downhill. If gravity were ever shown to originate from entropy, it would not diminish its elegance, but rather reveal that the universe organizes itself according to a profound balance of possibilities. Understanding this requires a shift in perspective. Physics often presents forces as fundamental, yet many forces we encounter emerge from collective patterns. The force that stretches a polymer arises because the chain has far fewer microstates when extended, so thermal fluctuations pull it into a more compact configuration. The osmotic force pushing water through a membrane depends on differences in microstate counts, rather than a direct mechanical influence. These are not analogies. They are real, measurable examples where forces emerge directly from entropy. They show that fundamental-looking behavior can arise from underlying statistics, even when nothing pushes or pulls in the traditional sense. Recognizing this helps us see how gravity might also be a manifestation of something deeper, though no claim of this kind has been demonstrated conclusively. If spacetime hides a microscopic structure, that structure must be subtle enough to preserve the smooth geometry we measure on everyday scales while still producing quantum fluctuations in extreme regimes. It must store information in ways that align with black hole thermodynamics, and it must cooperate with the equations of general relativity so precisely that deviations have remained undetected in all observations to date. Such a framework would need to explain how the curvature of spacetime arises from collective behavior, and why energy influences this curvature in exactly the way Einstein described. It would need to produce the equivalence of inertial and gravitational mass naturally, rather than requiring it as a postulate. These are difficult requirements, yet they do not place the idea beyond reach. Many successful physical theories began as attempts to reconcile what once seemed irreconcilable. The allure of emergent gravity grows stronger when we consider that the universe appears to store information in an unexpectedly economical way. The entropy of a black hole grows with the area of its horizon rather than the volume it encloses, a fact that still puzzles scientists decades after its discovery. This unusual scaling suggests that the true degrees of freedom responsible for gravitational behavior may live not in the bulk of space, but on surfaces or boundaries. Combined with hints from quantum entanglement and holography, this observation pushes many researchers to suspect that spacetime may be a kind of informational tapestry, woven from correlations between unseen components. Gravity, in such a picture, becomes a large-scale echo of how these components arrange themselves to satisfy deeper statistical laws. These ideas force us to confront the possibility that our familiar picture of space and time may be only an approximation, a grand emergent stage built from actors we have not yet identified. If so, the laws governing this stage might arise inevitably, much like the laws of fluid dynamics emerge from molecular chaos. We may think of gravity as the universe's most graceful expression of collective behavior, a phenomenon so universal that it appears fundamental even if its roots lie elsewhere. Yet scientists remain cautious. None of these ideas can replace general relativity, and none can match the cosmological successes of the current standard model of structure formation. Still, the hints are too persistent to ignore, and the search for deeper understanding continues not because we doubt relativity, but because nature keeps leaving clues that something even more profound may lie beneath it. As we move forward, entropy will play an increasingly central role. It will help us reinterpret the meaning of horizons, illuminate why black holes behave like thermodynamic objects, and reveal the surprising connection between information and geometry. Whether gravity turns out to be emergent or fundamental, These explorations open doors to unfamiliar landscapes where space-time is not a fixed backdrop, but a dynamic participant in the universe's statistical story. We are not seeking to replace Einstein. We are seeking to understand why Einstein's equations work so well and what they might be whispering about the reality hidden behind the smoothness of space. Entropy is a word that drifts easily through conversations, often carrying with it images of chaos or decay. Yet in physics, it carries a meaning far more precise and far more powerful. It is a measure of how many unseen microscopic configurations can correspond to the world we observe. When a system changes its state, when heat flows, when order melts into something more uniform, entropy is the silent accountant that tallies every possible arrangement. It is not a force, not a substance, not a physical particle drifting through space. It is a way of counting, a way of describing the likelihood of states, and a way of understanding why nature leans towards some outcomes more than others. To explore whether gravity could ever emerge from entropy, we must first understand the concept with clarity rather than metaphor, for nothing in this discussion can rest on loose interpretations or casual associations. Imagine a container filled with gas. At the microscopic level, the particles are moving in countless ways, each with its own speed and direction. We cannot track every particle, so we describe the system using averages such as pressure and temperature. Entropy measures how many different microscopic configurations could produce those same averages. A high entropy state is one with many possible arrangements, while a low entropy state is one with very few. When heat flows from a warm object to a cooler one, it is because the combined system has far more ways to organize itself after the energy has spread out. The process does not unfold because energy prefers to disperse, but because the number of microstates grows dramatically when it does. Entropy reveals that nature leans toward probability, not purpose. This link between entropy and probability becomes even more striking when we consider how systems behave near equilibrium. A system in equilibrium is one in which no net changes occur on the macroscopic level, yet the microscopic chaos remains ceaseless. Countless microstates are explored moment by moment, but the macroscopic state appears still because so many micro-configurations lead to the same large-scale properties. The system has reached a region where entropy is maximized under its constraints. If it is nudged away from that region, forces appear that drive it back toward equilibrium. These forces do not arise from mechanical pushes or pulls. They arise from the system's tendency to explore the vast landscape of microstates that correspond to equilibrium. This is the essence of an entropic force, and it is entirely measurable despite arising from no fundamental interaction. A familiar example is the elasticity of a polymer chain. When the chain is stretched, the number of microstates available to the system decreases because the molecular links must align into a more restricted configuration. When the tension is released, the system quickly snaps back toward a compact form because there are far more microstates in that region. The apparent restoring force is entropic, not mechanical. Another example appears in osmotic pressure, where water flows through a membrane toward a side containing solute particles. This flow occurs because the number of ways to arrange the solute and solvent together is greater than the number of ways to keep them separated. These behaviors demonstrate that entropy can create what appear to be forces, even though the underlying physics arises from counting possibilities rather than exchanging particles or fields. Understanding this opens a path toward thinking differently about gravity. If gravity were somehow related to entropy, it would not mean that gravitating bodies are decaying into disorder. Instead, it would mean that the motion of masses through space-time reflects the universe's tendency towards states that contain more microscopic configurations. The attraction between objects could arise because the configuration of space and matter has more available microstates when the objects move together than when they remain apart. This is not established physics, but it is a logical extension of what entropic forces already show us in well-understood systems. The key is that entropy is not a metaphor for randomness. It is a quantitative statement about how nature allocates its possibilities. To proceed carefully, we must also address how information enters the picture. In the mid-20th century, scientists such as Claude Shannon realized that entropy is not only a thermodynamic quantity, but also an informational one. Shannon entropy measures the uncertainty or information content of a message sent through a communication channel. It counts how many possible messages could have been received before the actual message was revealed. Although thermodynamic entropy and informational entropy arise in different settings, they share a deep mathematical structure. Both measure the logarithm of the number of possible outcomes consistent with the system's current state of knowledge. This connection does not mean that physical entropy and informational entropy are interchangeable, but it does mean that information theory provides a powerful language for thinking about physical systems where microstates matter. When physicists apply these ideas to the structure of spacetime, they discover that horizons behave like thermodynamic surfaces. Accelerating observers perceive a temperature in what others call vacuum. Black holes radiate as though they possess thermal properties, and the entropy associated with horizon scales with area rather than volume, an unusual and deeply revealing feature. These observations suggest that the gravitational field carries information in surprising ways, and that the microscopic degrees of freedom responsible for spacetime may be encoded on surfaces rather than throughout volumes. Although this is not a definitive proof of emergent gravity, it provides strong motivation to explore the idea that geometry and information may be related at a fundamental level. If entropy counts possibilities, and if gravitational phenomena appear connected to entropy in multiple unexpected contexts, then understanding the full meaning of entropy becomes essential for any attempt to understand gravity's origin. But to connect these ideas cleanly, we must investigate the setting where thermodynamics first touched spacetime in a truly unavoidable way. Black hole thermodynamics altered the conversation forever, revealing that the geometry of spacetime can carry entropy and temperature. To understand gravity's deeper nature, we must look closely at the horizons that hide information and the radiation that leaks from their edges. There, in the domain of black holes, the connection between entropy and gravity becomes unmistakable and impossible to ignore. The story of entropy becomes even more revealing when we examine how energy, temperature, and microscopic configurations relate to one another. In classical thermodynamics, temperature emerges as a measure of how easily a system's energy can spread among its available microstates. A warm object is not warm because it contains a special kind of energy, but because the energy contained within it can be rearranged in many subtly different ways. Entropy quantifies the number of those possibilities. Whenever heat flows between systems, it is because the combined arrangements become more numerous when energy is distributed more evenly. This principle is so reliable that it shapes the behavior of stars, controls chemical reactions, and governs the engines that power human civilization. It also provides the framework within which physicists later discovered that spacetime itself exhibits thermodynamic traits. To understand this connection, we must first dwell on the statistical meaning of entropy. Ludwig Boltzmann's great insight was that macroscopic quantities could be understood by counting microscopic arrangements. The temperature of a gas reflects the average kinetic energy of molecules that collide and rebound in countless ways. The pressure exerted by a gas arises from those collisions impinging upon a surface, and the entropy of the gas is proportional to the number of different microscopic configurations that share the same large-scale description. This interpretation ties the behavior of matter to probability. It tells us that nature explores its available configurations relentlessly, and that what we call the direction of time emerges from the fact that there are simply more ways for a system to be disordered than ordered when measured in microscopic detail. Although this reasoning first applied to matter, it extends far more broadly. Consider the simple act of mixing two substances. Once mixed, the entropy is larger because many more microscopic arrangements exist in which the particles are interspersed. The unmixing of the substances would require the system to find its way into an astronomically smaller set of arrangements. Since, Natural processes tend to move towards states with greater numbers of microstates. The direction of mixing is overwhelmingly favored. This tendency, so natural and intuitive once one becomes familiar with it, might at first seem distant from the behavior of gravity. However, the role entropy plays here is not about physical substances mingling. It is about the statistical structure of possible states, a structure that might underlie geometry itself. On the informational side, Shannon expanded the meaning of entropy by showing that messages, probabilities, and uncertainty obey rules mirroring thermodynamic quantities. His work revealed that when one transmits a message through a channel, the fundamental limit on compression depends on the entropy of the message distribution. Although this appears unrelated to physics at first glance, the parallel suggests that the universe may treat physical processes and informational processes with similar mathematical constraints. Information is not simply something we store on devices or send through wires. It is the currency of how systems encode and share the microscopic realities that support macroscopic behavior. If space-time contains deep informational structure, then entropy might provide one of the most direct windows into its organization. Hints of this structure appear in the study of accelerating observers. A curious result discovered in the 1970s showed that an observer accelerating through empty space should detect a thermal bath of particles even when an inertial observer sees none. This phenomenon arises because horizons form for the accelerating observer, limiting the region of space-time from which information can be received. The appearance of temperature in such a setting is not caused by the creation of new particles, but by the way information becomes inaccessible across that horizon. This observation, confirmed through analog experiments and consistent with quantum field theory, reveals that temperature and entropy can arise through the very structure of space-time, and not only through material interactions. Taken together, these developments show that entropy plays a dual role in physics. It counts microscopic states in matter as originally conceived, but it also measures the informational structure of space-time in the presence of horizons. This duality strengthens the idea that geometry and thermodynamics may be linked at a level deeper than classical theories suggest. It suggests that entropy may be woven into the behavior of space-time itself, guiding its evolution and influencing how systems move within it. If gravity emerges from statistical tendencies, the relevant tendencies may not involve particles alone, but also the informational constraints created by the geometry of space-time. Before we venture into the realm of black holes, where these ideas come fully into focus, it is useful to recognize that entropy's power lies in its universality. Whether one is studying a cup of water reaching room temperature, a gas expanding into a chamber, or a horizon concealing information, entropy serves as a guide to what nature allows and what it prefers. It does not dictate outcomes, but reveals which outcomes dominate the landscape of possibility. If gravity is linked to entropy, it would mean that the curvature of space-time is shaped not by geometric decrees alone, but by the statistical preference of the universe for certain microscopic configurations over others. This possibility is not a claim, but an open question, and answering it requires us to examine the domain where gravity and entropy meet most dramatically. Black hole thermodynamics has forced us to confront the fact that horizons possess entropy, that they radiate with temperature, and that the deep structure of space-time behaves like a thermodynamic system. To understand gravity's potential origins, we must explore that territory carefully, and it is to that terrain that our attention must now turn. The full importance of entropy in physics becomes clear when we examine the systems where microscopic uncertainty and macroscopic behavior intersect most dramatically. In every familiar thermodynamic process, entropy provides the compass that points toward the most probable states. But when scientists discovered that horizons in space-time behave thermodynamically, the role of entropy expanded into a realm where geometry itself seemed to participate in the counting of microstates. Long before black hole thermodynamics was fully understood, The principles of entropy already hinted that information and physical reality could not be separated as cleanly as once believed. What changed in the late 20th century was that these hints crystallized into precise mathematical statements showing that spacetime possesses entropy in a way that could not be ignored. One way to understand this is to consider what it means for a region of space to be inaccessible. When an observer accelerates uniformly, the boundary beyond which light can no longer reach them becomes a type of horizon. Quantum field theory predicts that such an observer will perceive a temperature associated with this horizon, even though an inertial observer perceives none. This effect shows that horizons create thermodynamic behavior without requiring any matter to be present. The temperature arises because certain modes of the quantum field become inaccessible, and the missing information transforms into thermal properties. Entropy therefore becomes not just a measure of states, but a measure of which states can be known. In this sense, entropy reflects both physical and informational structure, merging the two in a way that challenges the traditional separation between them. If entropy is linked to the limits of what can be known, then geometry gains a surprising new role. Horizons are geometric constructs, yet they impose informational constraints on observers. When black holes were first studied through the lens of quantum field theory, these constraints produced an even more astonishing result. Stephen Hawking discovered that black holes emit radiation with a temperature inversely proportional to their mass. This radiation implies that black holes obey thermodynamic laws similar to those of familiar systems. They possess entropy, temperature, and energy that change according to precise relationships. The entropy of a black hole scales with the area of its horizon rather than the volume contained within it, suggesting that the true microscopic degrees of freedom do not fill the interior, but reside near the horizon. This area scaling remains one of the most important clues in the quest to understand whether spacetime has an underlying microscopic structure. The appearance of entropy in black holes marks a turning point because it shows that spacetime itself must have microscopic degrees of freedom, even if we do not yet know what those degrees of freedom are. Entropy always counts possibilities, and if a horizon has entropy, then something must be counted. The question is what? Are the microstates fluctuations of quantum fields, patterns of entanglement, or something more exotic that has not yet been discovered? Whatever the answer, it must be compatible with the fact that black hole thermodynamics matches physical predictions with extraordinary precision. The existence of such entropy is not optional. It is required by the consistency of the theory. This realization reshapes how scientists think about gravity. If horizons behave thermodynamically, then perhaps the gravitational field is not fundamental but emergent from the collective behavior of the underlying microstates. This does not mean that gravity is illusory. It means that the shape and curvature of spacetime may reflect statistical rules that arise from deeper microphysics. Just as the pressure inside a gas is not a fundamental force, but a statistical effect of countless molecular collisions, the geometry of spacetime might be a statistical effect of the unseen components that give rise to it. The fact that entropy and temperature appear so naturally in gravitational contexts supports the idea that thermodynamics and geometry are deeply entwined. There is a subtle beauty in this viewpoint. Thermodynamics is a theory of information, probability, and irreversibility. Geometry is a theory of shape, distance, and curvature, yet both appear to describe facets of the same underlying reality. The more physicists investigate black holes, accelerating observers, and quantum fluctuations, the more they encounter entropy, not as an optional bookkeeping device, but as an unavoidable ingredient. Even the act of observing becomes intertwined with the structure of spacetime, suggesting that the universe may store information in ways that are inseparable from the geometry through which it unfolds. If gravity does emerge from entropy, the implications would stretch across the entire landscape of physics. The curvature of spacetime would reflect not only the distribution of energy, but also the way microstates arrange themselves beneath the surface of the world we know. The attraction between masses could be seen as a statistical bias towards certain configurations, an echo of nature's vast combinatorial structure. Yet this idea remains a hypothesis, not a claim. To pursue it further, we must turn to the phenomenon where thermodynamics first revealed itself as inseparable from gravity. That phenomenon is the thermodynamic behavior of black holes, where entropy and geometry intertwine so tightly that they cannot be separated. The path that leads from ordinary thermodynamics to the thermodynamic behavior of spacetime reaches its sharpest and most revealing point in the study of black holes. These objects, once imagined as simple gravitational traps from which nothing could escape, turned out to possess properties that mirror the behavior of familiar systems such as gases, liquids, and solids. Yet nothing about a black hole resembles those systems on the surface. A black hole has no molecules swirling inside it, no surface in the usual sense, and no internal structure that can be probed without crossing a boundary from which no signal can return. Despite these differences, black holes obey laws that look strikingly like thermodynamic laws. They have temperature, they have entropy, they exchange energy with their surroundings, and in doing so, they hint that gravity and thermodynamics are connected in a way no classical theory ever predicted. To appreciate how astonishing this discovery was, consider the expectations scientists once held. In classical general relativity, a black hole is simply a region of spacetime where the curvature becomes so strong that light cannot escape. The event horizon acts as a one-way boundary, not because it is made of matter, but because the geometry tilts inward so sharply that every path forward leads deeper into the interior. In such a picture, the horizon has no physical texture. It is simply the mathematical location where escape becomes impossible. Nothing about this description suggests a temperature or an entropy. Temperature is a concept tied to the motion of microscopic constituents. Entropy counts the number of ways those constituents can arrange themselves. But a black hole, according to the classical picture, contains no such constituents at its boundary. Its surface is purely geometric. The idea that it could behave like a hot object radiating particles would have seemed nearly unthinkable. The first hint that thermodynamics might apply to black holes emerged from thought experiments exploring how they interact with matter and energy. As researchers considered processes such as lowering objects toward a horizon or merging two black holes, they noticed patterns reminiscent of thermodynamic behavior. The area of a black hole's horizon never seemed to decrease in such processes, just as entropy never decreases in an isolated system. Energy flowing into a black hole caused its horizon to expand in a way that paralleled the relationship between heat and entropy. These similarities were compelling but still circumstantial. They suggested that black holes might follow rules resembling thermodynamic laws, yet they offered no temperature and no microscopic explanation. It remained unclear whether these parallels were deep truths or mathematical coincidences. The turning point arrived when Stephen Hawking applied quantum field theory to curved spacetime and discovered that black holes emit radiation. This radiation is not an approximation or a metaphor. It is a precise prediction arising from the interplay between quantum fluctuations and the geometry of the horizon. According to the theory, pairs of virtual particles constantly appear and disappear in the vacuum. Near the horizon, one member of the pair can fall inward while the other escapes to infinity. To an outside observer, this escaping particle appears as real radiation emitted by the black hole. The emission has a temperature determined by the black hole's mass, and this temperature is inversely related to the radius of the horizon. Large black holes radiate faintly. Small black holes radiate intensely. This phenomenon means that black holes are not perfectly black. They glow, they lose energy, and they evolve. Once Hawking radiation was discovered, the analogy with thermodynamics became unavoidable. If black holes have temperature, then they must possess entropy. Jacob Bekenstein had earlier proposed that black hole entropy should scale with the area of the horizon rather than the volume of the interior. Hawking's calculation confirmed this, showing that the entropy is proportional to the area measured in fundamental units. This area law remains one of the most profound clues in theoretical physics. It suggests that the true microscopic degrees of freedom underlying black hole entropy are arranged in a way that depends on surface area, not spatial volume. In ordinary matter, entropy grows with volume because the number of possible microstates increases as the system expands. Black holes behave differently. They store information in a manner that defies classical intuition, pointing toward a horizon-centered mechanism that no theory has yet fully explained. The four laws of black hole thermodynamics emerged soon afterward. They mirror the familiar laws of thermodynamics, but replace pressure, volume, and temperature with gravitational analogues. The surface gravity of a black hole plays the role of temperature. The horizon area plays the role of entropy. The total mass plays the role of internal energy. These parallels are so precise that they hint at a deeper principle connecting gravity and thermodynamics. They indicate that the Einstein equation, which describes curvature, may be intertwined with the same principles that govern heat and probability. In this light, the geometry of spacetime becomes more than a shape. It becomes a thermodynamic object whose behavior reflects the statistical tendencies of something hidden beneath. This realization forces us to reconsider what a horizon truly represents. It is not merely a place where escape becomes impossible. It is a surface that hides information, a boundary across which the microstates of the system cannot be accessed by an outside observer. The entropy associated with the horizon counts the number of underlying configurations that are consistent with what an external observer can know. In this sense, entropy does not represent disorder. It represents missing information, a limitation imposed by the very structure of space-time. This perspective extends seamlessly into the behavior of accelerating observers, who also encounter horizons and temperatures arising from the same underlying principles. It suggests that horizons and thermodynamics are inseparable, not because matter behaves oddly near them, but because geometry and information intertwine in fundamental ways. The implications of these discoveries reach far beyond black holes. They suggest that gravity itself may reflect statistical behavior governed by entropy, that space-time may be made of degrees of freedom whose collective tendencies mimic thermodynamic laws. Yet we cannot assume this is true without further evidence. Black hole thermodynamics provides clues, not conclusions. It tells us that entropy lives at the horizon and that temperature arises where geometry hides information. To follow these clues, we must explore how these ideas can be used to derive gravitational behavior, not merely observe it. That path leads to one of the most remarkable insights of modern physics, a demonstration that Einstein's equation may itself arise from thermodynamic principles. The deeper one looks into the thermodynamic behavior of black holes, the more clearly the connection between geometry and information begins to sharpen. A black hole seems, at first glance, to be a featureless object determined only by its mass, charge, and angular momentum. Yet the presence of entropy suggests that an astonishing number of microscopic configurations must exist behind the scenes, each contributing to the total count in a way that remains hidden from any observer outside the horizon. It is this hiddenness, this inaccessibility of information, that elevates the entropy of a black hole from a mathematical curiosity to a genuine physical quantity. What makes the situation remarkable is that the entropy is not stored in the volume of the black hole, where intuition might place it, but in the surface area of the horizon. This unusual scaling hints that the fundamental degrees of freedom of spacetime may be arranged holographically, as though the fabric of reality compresses information into fewer dimensions. This idea grows even more compelling when we examine how the laws of black hole mechanics mirror the laws of thermodynamics. When energy crosses a horizon, the surface area increases in a way that resembles the rise of entropy when heat flows into a system. The surface gravity, which measures the acceleration needed to remain stationary near the horizon, plays the role of temperature, The relationship between mass and area echoes the relationship between internal energy and entropy. These parallels were initially puzzling, but once Hawking radiation was derived, they took on a new inevitability. If a black hole radiates like a hot object, then its horizon must behave like a thermodynamic boundary. If the boundary has entropy, then it must count microstates. And if microstates exist, then spacetime cannot be fundamental in the classical sense. Something must lie beneath, something that assigns microscopic degrees of freedom to what appears, on larger scales, to be empty geometry. To understand the significance of Hawking radiation more fully, consider the role of quantum fluctuations near the horizon. Vacuum is not empty. It teems with transient particle pairs that appear and vanish in accordance with quantum uncertainty. Near a horizon, these fluctuations are disrupted by the geometry. When one particle falls inward and the other escapes, the black hole loses a tiny amount of mass. Over immense timescales, this process slowly evaporates the black hole. The temperature of this radiation depends on the surface gravity, meaning that the geometry itself sets the temperature. This is unlike any traditional thermodynamic system, where temperature arises from the properties of matter. Here, temperature emerges from curvature, from the way spacetime bends. The idea that geometry can determine temperature had once seemed inconceivable, yet it arises naturally when quantum theory is applied to curved spacetime. This interplay between quantum fields and geometry illustrates a point of profound importance. The vacuum state is not absolute. Different observers, moving along different paths, do not agree on what counts as empty space. An inertial observer sees a quiet vacuum, while an accelerating observer perceives a warm bath of particles. The temperature that emerges for the accelerating observer, known as the Unruh temperature, depends only on the acceleration. This effect, though difficult to measure directly, is supported by theoretical consistency and by analog experiments performed in condensed matter systems. Its significance is immense. It suggests that thermodynamics appears whenever information is restricted by horizons, whether those horizons belong to black holes, accelerating observers, or cosmological expansion. Entropy and temperature follow the horizon, not the object. They arise because the horizon hides information in a way that forces the system to adopt a thermodynamic description. This realization changes how we think about horizons themselves. A horizon is not a physical surface. It is a boundary in knowledge, a place where information becomes inaccessible. The entropy associated with that boundary counts how many different microscopic configurations are consistent with what an observer outside the horizon can know. This is a shift in perspective with far-reaching implications. It suggests that entropy is fundamentally tied to information, and that information is tied to geometry. The structure of spacetime, the shape of horizons, and the thermodynamic behavior of gravitational systems may all reflect choices made by nature at a microscopic level, choices we can glimpse only through their macroscopic consequences. The area law, which states that black hole entropy grows with the area of the horizon, stands as one of the most important clues in theoretical physics. The simplicity of the scaling conceals its extraordinary depth. Why area? Why not volume? Why should the entropy of a region of space depend on its boundary instead of the amount of space contained within? These questions hint that our familiar understanding of locality may be incomplete. Perhaps the degrees of freedom that define spacetime are arranged in lower dimensional structures, or perhaps the entanglement of quantum fields across the horizon encodes information in a way that naturally produces an area law. Whatever the underlying explanation, the appearance of entropy tied to geometry demands that we rethink what spacetime is made of. As researchers pursue these questions, the behavior of black holes becomes a laboratory for ideas about quantum gravity. Every thermodynamic property they exhibit pushes us toward the conclusion that geometry is not a passive stage, but an active participant, shaped by deeper currents of information. The fact that black holes behave like thermodynamic objects reveals that spacetime contains more structure than classical physics suggests. That structure may hold the key to understanding why general relativity works and how it connects to quantum theory at the smallest scales. The insights gained from black hole thermodynamics do not merely refine our theories, they challenge the very notion of what constitutes a fundamental explanation. As scientists probed deeper into the thermodynamic behavior of black holes, they began to realize that these objects offer a rare glimpse into the structure of nature at its most extreme. Nothing else in the universe combines quantum effects, thermodynamics, and spacetime geometry with such clarity. A black hole compresses everything that falls into it so drastically that classical descriptions collapse under their own weight. Its horizon divides what is knowable from what is forever hidden, and its entropy, tied to the area of that horizon, stands as a constant reminder that the true microscopic degrees of freedom of spacetime must exist even if we have not yet uncovered them. These clues form a constellation of ideas pointing toward the same destination. Something lies beneath geometry, and whatever that something is, must be capable of producing the thermodynamic properties we observe. This insight becomes particularly striking when we consider the fate of information that falls into a black hole. Classical general relativity predicts that once something crosses the horizon, all details about it vanish from the outside world, except its mass, charge, and angular momentum. Yet quantum mechanics insists that information cannot be destroyed. This tension between the two theories is known as the information paradox, and it signals that our current understanding of gravity is incomplete. Hawking radiation seems to allow black holes to evaporate. But if the radiation carries no information about what fell in, then information appears to be lost forever. Resolving this puzzle has become one of the most important challenges in modern theoretical physics. Many proposed solutions rely on the idea that space-time is not fundamental but emergent, and that information is encoded in ways that classical geometry cannot display. The more we study horizons, the more we find that information, entropy, and geometry are inseparable. Quantum entanglement across the horizon contributes to the entropy of the black hole. The smoothness of the horizon, as perceived by falling observers, depends on delicate patterns of entanglement that connect interior and exterior regions. Even the evaporation of the black hole can be interpreted in terms of changing correlations between quantum fields. All of these features suggest that the interior of a black hole and the region outside it are not separate in the way classical geometry implies. Instead, they may be connected through patterns of quantum information that weave the structure of spacetime together. If this is correct, then gravity may be the large-scale manifestation of the way these patterns organize themselves across horizons and throughout the universe. The idea that geometry might emerge from information is bold, but black hole thermodynamics gives it weight. If entropy counts microstates and black holes carry entropy, then spacetime must contain microstates. If temperature appears at horizons and depends on surface gravity, then geometry must influence thermal behavior. And if the area law holds so universally, then whatever the underlying degrees of freedom are, they must arrange themselves in a way that reflects surfaces rather than volumes. These observations do not tell us what the microstates are, but they tell us that they exist and that they give rise to thermodynamic behavior in gravitational settings. The bridge between thermodynamics and geometry is not an analogy. It is a physical connection revealed through precise calculations. This connection becomes a stepping stone toward theories that attempt to derive gravity itself from thermodynamic principles. If the Einstein equation that defines how space-time curves can be shown to emerge from entropy and energy flow, then gravity may be understood as an equation of state rather than a fundamental interaction. This possibility gained serious consideration when a remarkable result demonstrated that the familiar geometric description of gravity could arise naturally from the thermodynamic behavior of microscopic degrees of freedom. The idea is not that space-time is made of heat or that black holes literally behave like conventional thermodynamic objects. It is that the same logic governing heat flow in ordinary systems may also govern the behavior of spacetime when viewed from the right perspective. To explore this, we will turn next to a profound insight that transformed the conversation about emergent gravity. It shows that Einstein's equations may not need to be postulated. They may instead be derived, appearing as a natural consequence of the deep relationship between entropy, energy, and spacetime. This insight does not prove that gravity is emergent, but it demonstrates that thermodynamics and geometry are so deeply entangled that separating them may no longer make sense. It opens a doorway into a new way of thinking, one where gravity could be understood not as a fundamental command of nature, but as the statistical behavior of something hidden beneath the smooth surface of spacetime. The idea that gravity might emerge from deeper statistical behavior gained its most striking and mathematically precise support when Ted Jacobson made a discovery that reshaped how physicists think about spacetime. Instead of treating Einstein's equation as a fundamental law, he asked whether it might arise the way the laws of thermodynamics arise, as a relationship connecting heat, entropy, and energy flow. This was not a speculative metaphor, but a concrete calculation built on the behavior of horizons, entropy, and the local structure of spacetime. Jacobson's insight was simple in spirit, yet profound in consequence. If every point in spacetime possesses a local horizon from the viewpoint of certain observers, and if those horizons obey the familiar relation between heat and entropy, then perhaps the curvature of spacetime is nothing more than the thermodynamic response of some underlying microscopic degrees of freedom. In this view, gravity becomes the large-scale echo of microscopic processes that we cannot yet see directly. To understand the logic of Jacobson's argument, imagine choosing any point in spacetime and examining it from the perspective of an observer who accelerates just enough to produce a local horizon. This is always possible because small regions of spacetime behave almost like flat space, and an accelerating observer in flat space perceives a horizon across which information becomes inaccessible. The observer also perceives a temperature proportional to their acceleration, a phenomenon known as the Unruh effect. By considering a narrow bundle of light rays that generate this local horizon, Jacobson argued that any energy flowing across this boundary carries heat, and any change in the area of the boundary corresponds to a change in entropy. Using the relation between heat flow and entropy change, he connected the expansion or contraction of the horizon to the energy passing through it. The remarkable result was that this relation reproduces Einstein's equation exactly when the entropy is proportional to the area of the horizon. This means that the equation describing how matter curves space-time can be rewritten as a thermodynamic equation of state. In ordinary thermodynamics, an equation of state connects variables such as pressure, temperature, and volume. It does not describe fundamental particles, but the macroscopic behavior of an underlying microscopic system. In Jacobson's picture, the curvature of spacetime emerges in the same way, as a description of the collective behavior of degrees of freedom, whose details remain unknown. The insight is powerful because it shows that gravity may not be fundamental, even if the equations describing it are accurate. It opens the door to the possibility that spacetime is made of something more basic, something that arranges itself in ways that mimic the geometric laws Einstein discovered. The elegance of this argument lies in its restraint. Jacobson did not propose a specific, microscopic model of spacetime. He did not speculate about strings, loops, or particles' underlying geometry. Instead, he showed that if entropy is proportional to area, and if energy flow across local horizons obeys the usual thermodynamic rule, then the Einstein equation follows automatically. This result does not mean that gravity is entropic in the everyday sense. It does not prove that spacetime is literally a thermodynamic fluid or that heat drives the curvature of the universe. What it demonstrates is that the structure of Einstein's equation is compatible with, and perhaps required by, the thermodynamic behavior of horizons. It suggests that the laws of gravity reflect deeper informational and statistical principles, and that geometry itself may be governed by the same logic that drives heat exchange. One of the most compelling aspects of Jacobson's insight is its independence from any specific theory of quantum gravity. Whether spacetime is composed of quantum loops, vibrating strings, causal sets, or entangled networks, the thermodynamic reasoning remains valid as long as entropy scales with area and horizons behave according to established principles. This universality hints that thermodynamics may be a bridge connecting different approaches to quantum gravity. It also suggests that entropy and information may be the most fundamental ingredients from which spacetime is assembled. Instead of viewing gravity as a force among particles, we can view it as a constraint arising from the organization of microstates, a constraint that appears as geometry at large scales. This perspective becomes even more compelling when one considers how entanglement entropy fits into the picture. In quantum field theory, entanglement between regions separated by a boundary naturally produces an entropy proportional to the area of that boundary. This behavior mirrors the entropy of black holes, suggesting that the area law may arise from the entanglement of microscopic degrees of freedom. If this is correct, then Jacobson's argument gains additional depth. The curvature of spacetime may reflect how entanglement changes when energy flows from one region to another. Geometry may be shaped by the distribution and reorganization of quantum correlations, not by a fundamental gravitational force. These ideas do not overthrow general relativity. Instead, they enrich it. Einstein's equation remains accurate on large scales, but its meaning changes. Rather than a fundamental law, it becomes a macroscopic description, like the equations governing fluid flow or elasticity. What we perceive as curvature may be the thermodynamic response of a deeper substrate. This does not diminish the elegance of relativity. It enhances it, revealing that its mathematical beauty may arise from statistical harmony rather than geometric decree. To appreciate the full depth of Jacobson's reasoning, we must look more closely at the role of local horizons and why they are central to his argument. In general relativity, the structure of spacetime near any point can be approximated by a locally flat region, much like a tiny patch of the Earth appears flat, even though the planet is curved. Within this small neighborhood, an observer who accelerates will perceive a horizon that blocks information from a portion of spacetime. This horizon is not a physical surface, but a limit of accessibility. The accelerated observer loses contact with events beyond it, and that loss of access produces thermodynamic consequences. The observer perceives a temperature associated with the horizon, and the flow of energy across that boundary corresponds to heat flow. This is the essence of the Unruh effect, and it provides the foundation upon which Jacobson built his thermodynamic interpretation of gravity. Once this local structure is in place, Jacobson considered the area of the horizon and how it changes as energy passes through it. The Einstein equation relates energy and curvature affects how bundles of light rays converge or diverge. These light rays generate the local horizon. If energy flows across the horizon, the curvature in the region changes slightly, altering the expansion of the light rays and therefore changing the horizon area. Because the horizon has entropy proportional to its area, any such change must correspond to a change in entropy. This forms the bridge between geometry and thermodynamics. The heat flow is determined by how much energy crosses the horizon, and the entropy change is determined by how the horizon area shifts. Equating the two in the familiar thermodynamic relation yields the Einstein equation as a direct consequence. This approach marks a conceptual turning point because it explains something once taken as fundamental by deriving it from more primitive notions. The Einstein equation becomes a statement about how entropy responds to energy flow, not a decree about how spacetime must curve. The curvature of spacetime behaves like a thermodynamic variable, adjusting itself to maintain consistency with the underlying statistical structure. This does not mean that spacetime is literally made of particles jostling like molecules in a gas. Rather, it means that geometry may be a coarse description of something whose details we cannot resolve. Hidden beneath the smoothness of spacetime could be a complex network of degrees of freedom whose collective behavior manifests as curvature and gravitation. Such a view gains further support from the behavior of quantum entanglement. When a quantum system is divided into two regions, entanglement between the regions produces an entropy that depends on the boundary between them. This area scaling is reminiscent of black hole entropy and suggests that the entropy associated with horizons may arise naturally from entanglement among microscopic degrees of freedom. If this is the case, then Jacobson's assumption that entropy is proportional to horizon area is not an arbitrary choice but a reflection of the deep structure of quantum fields. Entanglement entropy becomes a candidate for the microscopic origin of spacetime thermodynamics, linking information and geometry even more tightly. One of the most striking aspects of Jacobson's argument is its emphasis on locality. Instead of focusing on entire black holes or cosmological horizons, he looked at infinitesimal patches of spacetime. Every point, in his view, contains the seeds of horizon thermodynamics. This means that gravitational dynamics arise everywhere, not just near extreme objects. The behavior of spacetime at each point reflects the same relationship between entropy and energy flow. This universal applicability reinforces the idea that gravity may be emergent. If the same thermodynamic logic applies at every location, then gravitational curvature becomes a large-scale expression of microscopic statistical rules, rather than a feature requiring unique underpinnings in different environments. The consequences of this perspective ripple outward. If gravity is emergent, then quantizing it directly may be misguided. Just as one does not quantize the Navier-Stokes equations to learn about water molecules, one might not quantize the Einstein equation to learn about the microscopic structure of spacetime. The appropriate route would instead be to identify the microstates whose statistical behavior produces the Einstein equation at large scales. This viewpoint reshapes the pursuit of quantum gravity, encouraging researchers to search for theories where geometry emerges from entanglement, information, or algebraic structures rather than treating geometry as fundamental. Jacobson's insight has inspired numerous developments in the decades since it was proposed. Some researchers have explored how entanglement variation among neighboring regions of space can reproduce gravitational dynamics. Others have used ideas from quantum information theory to reconstruct portions of spacetime from boundary data in controlled settings. These efforts all share a common thread. They treat gravity not as a force to be quantized, but as a thermodynamic phenomenon arising from deeper degrees of freedom. This approach does not reject general relativity, but reframes it, placing it within a hierarchy of descriptions where the geometric laws we observe emerge from more fundamental principles. Yet, even as these ideas flourish, they remain incomplete. Jacobson's argument relies on assumptions about entropy and energy flow that are motivated by black hole thermodynamics, but not yet derived from a microscopic theory. It shows that space-time dynamics are consistent with thermodynamic principles, but does not reveal the microstates themselves. The search for those microstates continues, extending across multiple research programs that attempt to unify quantum mechanics and gravitation. Each program offers clues, and many of those clues point back toward the same themes. Entanglement seems to play a central role. Horizons seem to encode information, and the area law for entropy appears again and again as a signature of something deeply woven into the structure of reality. The strength of Jacobson's insight lies in how it reframes familiar ideas without discarding any of the experimentally confirmed features of general relativity. Nothing in his reasoning contradicts the bending of starlight, the slowing of clocks in strong gravitational fields, or the gravitational waves that ripple through the cosmos when massive bodies collide. Instead, it offers a deeper explanation for why these phenomena occur. If geometry is not fundamental, but arises from the statistical behavior of microscopic degrees of freedom, then the elegance of Einstein's equations becomes a reflection of the hidden order that emerges when immense numbers of microstates act collectively. Just as fluid dynamics emerges from countless molecular motions, yet displays smooth and predictable patterns, gravity might emerge from unseen informational or quantum interactions that similarly produce a coherent, large-scale geometry. This idea does not lessen the grandeur of general relativity. Rather, it enriches it by revealing that the curvature of spacetime may encode an entire thermodynamic language beneath its surface. The familiar image of spacetime as a smooth fabric becomes more intricate, more textured. Each curve, each horizon, each ripple in the geometry may signal a shift in the underlying microstructure, a reshaping of the informational degrees of freedom that gives spacetime its form. If the Einstein equation is an equation of state, then the universe behaves not as a rigid geometric stage, but as a dynamic medium whose properties reflect the statistics of its fundamental constituents. This perspective bridges what once seemed separate realms, linking geometry with thermodynamics and thermodynamics with information. One of the clearest indications that this approach has deep merit is that it finds harmony with insights gained from quantum field theory and quantum information science. When physicists compute the entanglement entropy of a quantum field divided into two regions, the result grows with the area of the dividing boundary. This striking similarity to black hole entropy suggests that the area law may reflect universal features of quantum systems rather than peculiar properties of gravity. If the entanglement between microscopic degrees of freedom naturally produces an entropy proportional to area, then the entropy assigned to horizons may arise from these same correlations. Geometry may simply provide the macroscopic canvas upon which entanglement patterns are projected. Such reasoning aligns with the growing belief that spacetime itself may emerge from networks of quantum entanglement. In this picture, distances and curvature reflect how information is shared and distributed across these networks. Regions that are strongly entangled appear close. Regions that are weakly entangled drift apart. Horizons form where entanglement patterns break, and the entropy associated with those horizons counts the number of underlying configurations consistent with the visible geometry. Although this picture remains speculative, it resonates strongly with Jacobson's thermodynamic derivation, suggesting that entanglement may provide the microscopic foundation required to turn thermodynamic principles into geometric laws. Yet, for all its elegance, Jacobson's approach leaves many questions unanswered. If the Einstein equation arises from thermodynamics, then what is the fundamental theory from which this thermodynamics emerges? What are the microstates counted by black hole entropy? How do these microstates behave, interact, and organize themselves to produce the smooth and continuous geometry we observe? Without answers to these questions, the picture remains compelling but incomplete. Emergent gravity offers a framework, not a finished theory. It shows what gravity could be, not what it must be. Still, the influence of Jacobson's insight persists because it offers a fresh way to interpret the long-standing puzzle of gravity's relationship with quantum mechanics. Instead of forcing geometry into a quantum framework by treating spacetime as another field to quantize, his approach invites a reversal of perspective. Perhaps gravity is classical because it is emergent, not because it resists quantum interpretation. Perhaps the deep quantum behavior lies not in the geometry itself, but in the microscopic degrees of freedom from which geometry arises. If so, then the incompatibility between general relativity and quantum mechanics may stem from the fact that they describe different layers of reality. One describes the macroscopic thermodynamic behavior of spacetime. The other describes the microscopic interactions underpinning that behavior. This shift in perspective helps clarify why attempts to quantize gravity directly have proven so difficult. Quantizing an emergent phenomenon can obscure rather than illuminate the underlying physics. The quantum properties of water do not become clearer by quantizing the equations of fluid flow. To understand the microscopic behavior of water, one must examine individual molecules and their interactions. By analogy, to understand the microstructure behind spacetime, one must look beneath the Einstein equation rather than extending it. Jacobson's work encourages this approach, guiding the search toward theories where geometry emerges from statistical and informational principles rather than serving as an immutable foundation. In the decades since Jacobson presented his insight, researchers have expanded upon it, exploring how variations in entanglement entropy can reproduce gravitational dynamics in broader contexts. These developments strengthen the idea that gravity may be intertwined with quantum information at a fundamental level, even if emergent, even if gravity is not the final answer. It illuminates a path toward unifying the thermodynamic, quantum, and geometric aspects of nature. It suggests that the universe may be organized according to principles that become visible only when we look at how information flows, how entropy changes, and how geometry adapts accordingly. The idea that gravity might emerge from entropy gained renewed public and scientific attention when Verlinde proposed a bold and imaginative framework, suggesting that gravitational attraction could arise from changes in information associated with the positions of material bodies. Verlinde's approach began with a simple yet far-reaching question. If entropy and information play such important roles in black hole thermodynamics and horizon behavior, could these same principles extend to ordinary gravity? Could the familiar pull between masses be a manifestation of entropic tendencies rather than a fundamental interaction? The question itself was provocative, not because it challenged general relativity directly, but because it reframed gravity in terms of information and statistical behavior. Verlinde's argument did not replace Einstein's theory, but it offered a different lens through which gravitational phenomena might be interpreted. His starting point was the notion that when a particle approaches a surface storing information about its position, the number of accessible microstates changes. If the number of microstates increases when the particle moves in a particular direction, then an entropic force arises that appears to push or pull the particle. This is similar to how springs, polymers, and other entropic systems behave. In Verlinde's formulation, space itself acts as a kind of information storage system, and the motion of matter through space reflects how this information changes. The fascinating aspect of this approach is that, under specific assumptions, one can recover Newton's inverse square law of attraction between masses. The force of gravity appears not as a fundamental exchange between objects, but as a thermodynamic consequence of how information reorganizes when matter changes position. Although this reasoning captured wide interest, its strength lies more in its conceptual boldness than in its empirical support. Verlinde's argument relies heavily on the assumption that holographic screens, hypothetical surfaces that encode information about the positions of objects, behave in a particular way. These screens are not part of any established theory, but serve as a mathematical device to explore how information might be distributed in spacetime. By assuming that changes in entropy on these screens correspond to the displacement of masses, Verlinde derived classical gravitational behavior. However, the assumptions underlying these derivations were not derived from deeper theories, but introduced to make the calculations work. This leaves the proposal intriguing but speculative, resting on a foundation that still lacks microscopic justification. Despite these uncertainties, Verlinde extended his ideas further by attempting to address one of the most persistent mysteries in astrophysics, the missing mass problem. Galaxies rotate faster than their visible matter should allow. Galaxy clusters exhibit gravitational effects far beyond what their luminous mass can produce, and the cosmic microwave background displays patterns best explained by large amounts of invisible matter. The prevailing explanation is that the universe contains dark matter, a form of matter that interacts gravitationally but not with light. Verlinde proposed that instead of invoking unseen particles, these effects might arise from the interplay between matter, entropy, and the geometry of space on large scales. In his framework, gravity acquires an additional component at galactic distances, emerging from information associated with the distribution of mass and the expansion of the universe. This alternative to dark matter produced both excitement and skepticism. On the one hand, it offered a novel perspective that attempted to link cosmology, thermodynamics, and information in a unified picture. On the other hand, it struggled to match the precision of observations that the dark matter model explains well. The rotation curves of galaxies can be approximated in Verlinde's framework, but the behavior of galaxy clusters, gravitational lensing patterns, and the structure of the cosmic microwave background all present significant challenges. The dark matter model, despite its mysteries, fits these data with impressive accuracy. Verlinde's entropic gravity, by contrast, remains incomplete in explaining these large-scale phenomena. The scientific community views Verlinde's proposal as an interesting hypothesis rather than a replacement for general relativity or the dark matter paradigm. It offers a stimulating avenue for research, encouraging scientists to explore whether information and entropy could play broader roles in gravitational dynamics. Yet it does not currently match the predictive power or empirical success of established models. The assumptions behind the holographic screens have not been derived from any known microscopic theory, and it remains unclear whether they can be reconciled with the wealth of observational evidence supporting dark matter. Still, Verlinde's contribution is valuable because it expands the conceptual landscape. By showing how gravity might be reinterpreted through informational and thermodynamic reasoning, he invites the scientific community to consider alternatives that might one day connect general relativity with quantum theory in unexpected ways. Even if the entropic force model does not describe the true nature of gravity, its emphasis on information and statistical behavior aligns with deeper trends emerging from black hole thermodynamics, quantum field theory, and holographic dualities. In this sense, the proposal serves as a bridge between established knowledge and speculative exploration. To understand both the promise and the limitations of Verlinde's proposal, it helps to examine the logic that leads from information to gravity in his framework. He begins by imagining that space is not a static stage, but a storage system for information associated with the positions of material bodies. When matter moves, the information distribution changes, and this reorganization affects the number of microstates available to the system. An entropic force arises whenever the number of accessible microstates increases or decreases in a way that guides the motion of matter. The key idea is that nature tends towards states with a greater number of microscopic configurations, and this statistical tendency manifests as motion that resembles gravitational attraction. Under the right assumptions, this entropic tendency produces a force that mirrors Newtonian gravity. One can see why this perspective attracted interest. It brings gravity into the domain of thermodynamics and information, two areas that have become increasingly important in modern physics. By suggesting that the motion of matter arises not from a fundamental interaction, but from entropy gradients, the theory challenges conventional thinking while remaining mathematically simple. It evokes the behavior of well-understood systems such as polymer chains and osmotic flows, where effective forces arise without any underlying exchange of particles. This conceptual clarity gives the proposal an intuitive appeal. It suggests that gravity might be an emergent phenomenon, a statistical effect of deeper informational structures that shape the geometry of space. Yet this appeal is tempered by the assumptions required to reach the result. Verlinde introduces holographic screens, imagined surfaces that encode information about the positions of particles, much like black hole horizons, encode information about events behind them. But unlike the horizons of black holes, which follow directly from the geometry of spacetime, these holographic screens do not arise naturally in the theory. They must be assumed. Their information content must be assumed. Their thermodynamic properties must be assumed, and the manner in which they respond to the motion of matter must also be assumed. These assumptions do not make the theory invalid, but they limit its explanatory power. Without a microscopic model to support them, the holographic screens function as conceptual tools rather than predictions of a deeper framework. Despite this, Verlinde expanded his idea to address galactic dynamics by proposing that the stretching of spacetime due to cosmic expansion modifies the entropy associated with mass distributions. This modification produces an additional apparent gravitational effect at large distances. one that could mimic the influence of dark matter. In this view, galaxies rotate as they do not because of invisible particles, but because the entropy associated with the distribution of matter and the expansion of the universe generates an emergent force. This idea is elegant in its ambition. It ties together cosmological expansion, entropy, and gravitational behavior within a single conceptual scheme. However, elegance must yield to evidence. The predictions derived from Verlinde's extended framework can reproduce certain galactic rotation curves with reasonable accuracy, but they struggle with several lines of observational data. Galaxy clusters exhibit gravitational lensing that far exceeds what is expected from visible matter, and Verlinde's model has difficulty reproducing this behavior. The cosmic microwave background, which encodes the earliest structural seeds of the universe, matches the predictions of the dark matter model with extraordinary precision. Verlinde's approach does not naturally reproduce these patterns. Furthermore, the distribution of galaxies on the largest scales, the formation of cosmic filaments, and the dynamics of colliding clusters all align with the presence of dark matter, but present significant challenges for the entropic gravity model. These limitations do not diminish the creativity of the proposal, but they highlight the distinction between conceptual appeal and empirical success. Science demands that theories not only explain known phenomena, but also withstand the scrutiny of new observations. In this regard, Verlinde's entropic gravity remains an intriguing possibility, searching for a stronger foundation. It has not been ruled out in all contexts, but it has not demonstrated the predictive accuracy required to replace the current dark matter paradigm. Instead, it lives in a space between inspiration and verification, a reminder that imaginative ideas can propel the field forward even when they are not yet supported by evidence. Still, the value of Verlinde's work extends beyond its immediate predictions. It emphasizes the role of information, entropy, and holography in thinking about gravity. It aligns with themes emerging from black hole thermodynamics and from holographic dualities in theoretical physics. Even if the specific details of the proposal do not survive future scrutiny, its underlying motivation resonates with broader trends. The idea that gravity may arise from informational structure rather than fundamental fields reflects a shift occurring across many research directions, from quantum gravity to condensed matter analogies. The discussion surrounding Verlinde's ideas highlights an important truth about modern theoretical physics. New proposals often serve less as replacements for established frameworks and more as catalysts that expand the range of questions scientists are willing to ask. Verlinde's approach does not overthrow general relativity, nor does it eliminate the need for dark matter, but it encourages researchers to reconsider the assumptions they make about gravity and the role of information in shaping physical law. By suggesting that gravitational dynamics might arise from entropy changes rather than a fundamental interaction, it shifts attention toward the possibility that spacetime itself may be the macroscopic expression of deeper microscopic relations. Even if these ideas ultimately evolve into something different, the conceptual space they open remains valuable. Part of this value lies in the way Verlinde's proposal connects gravitational behavior with the holographic principle, a concept arising from black hole thermodynamics that suggests the information content of a region of space might be encoded on its boundary. In Verlinde's formulation, holographic screens play a central role. They act as repositories for information about matter, and the way this information changes determines how matter moves. While the screens remain hypothetical constructs, the intuition behind them resonates with the holographic principle's deeper message. If the universe fundamentally encodes information on surfaces rather than volumes, then gravitational phenomena may reflect the architecture of this encoding. Verlinde's screens may not be the correct implementation, but they point toward a direction where gravitational behavior emerges naturally from informational constraints. Another important aspect of Verlinde's work is its connection to the idea that cosmological expansion may influence gravitational dynamics. His extended theory attempts to incorporate the large-scale structure of the universe into a local description of gravity, suggesting that as the cosmos expands, it alters the entropic conditions under which matter interacts. This notion resonates with broader efforts to understand why dark energy and dark matter dominate the evolution of the universe. Even if Verlinde's interpretation does not survive detailed comparison with observations, the idea that cosmic expansion and entropy are intertwined may still play a role in deeper theories of gravity and cosmology. Crucially, the scientific community has not embraced Verlinde's proposal as a competing theory to general relativity. Instead, it is recognized as a creative exploration of how gravity might be reinterpreted in the light of thermodynamics and information theory. Many criticisms focus on the lack of a concrete microscopic model supporting the entropic assumptions, the difficulties in matching precise observational data, and the need for stronger derivations connecting holographic ideas to realistic spacetime geometries. These critiques reflect the healthy skepticism that drives scientific progress. A theory must be tested against nature, and when it struggles, it must either adapt or yield to better supported frameworks. Even so, the ideas introduced by Verlinde continue to influence research. They encourage deeper investigations into how information and entropy shape physical systems, and they highlight the possibility that gravity may be less fundamental than once believed. They also draw attention to the puzzling behavior of entropy in gravitational contexts, especially the area scaling of black hole entropy and the entropic structure of horizons. These puzzles remain unsolved, and any theory capable of explaining them consistently would mark a significant breakthrough. In this sense, Verlinde's contribution is not measured solely by how closely his predictions match observations, but by how effectively the proposal inspires new questions. What is the microscopic structure that gives rise to black hole entropy? How does entanglement create geometry? Why does spacetime respond to energy in such a precise way that its curvature reproduces Einstein's equation? Whether gravity is emergent or fundamental, these questions point toward the frontier where quantum theory, thermodynamics, and cosmology meet. They remind us that profound ideas often begin as imperfect sketches, and that exploring them can lead to insights even when their initial form does not survive. The idea that the universe might encode its information on surfaces rather than within volumes began as a surprising proposal, but has since grown into one of the most influential concepts in theoretical physics. The holographic principle emerged from attempts to understand why black hole entropy scales with the area of the horizon rather than the volume contained within it. This area law, discovered through the study of black hole thermodynamics, suggested that the number of possible microstates associated with a given region of space does not grow with the amount of space, but with the size of its boundary. Such a conclusion runs against everyday intuition, where the number of ways to arrange matter typically increases with the volume available. Yet, when the universe reveals a pattern that contradicts our expectations, the proper response is not to dismiss the pattern, but to understand what deeper principle might produce it. The foundations of the holographic principle were laid when researchers realized that black holes limit the amount of information that can be stored within a region. If too much matter or energy is compressed into a finite space, a black hole forms, and the information about the internal configuration becomes hidden behind the horizon. The maximum amount of information that can be stored in that region is therefore set by the area of the horizon that would surround it, not the volume contained within. This is a profound restriction. It implies that the universe cannot store arbitrary amounts of information in arbitrary amounts of space. There is a fundamental limit, and that limit depends on surface area. Such a result would make little sense if spacetime were built from independent degrees of freedom located at each point in the interior. It hints instead that the true degrees of freedom may live on lower dimensional structures. This insight was deepened by the work of Gerard 't Hooft and Leonard Susskind, who proposed that the physics inside a region might be fully described by information encoded on its boundary. This does not mean that the boundary is a physical membrane, but that the mathematical description of the system may be equivalent to a description defined on one fewer spatial dimension. The term holographic refers to this reduction, similar to how a hologram stores three-dimensional information on a two-dimensional surface. If this principle holds generally, then spacetime itself may be emergent from degrees of freedom living on boundaries, and the curvature we observe could be a consequence of how these boundary degrees of freedom organize and entangle. The most striking confirmation of holographic ideas came from the development of the correspondence between a gravitational theory inside a negatively curved spacetime and a quantum field theory defined on its boundary. This duality, known as ADS-CFT, revealed that a complete description of a gravitational system in a particular type of spacetime is mathematically equivalent to a theory with no gravity living on a lower dimensional boundary. The correspondence is exact in this setting, meaning every physical quantity in the gravitational theory corresponds to something in the boundary theory. This discovery provided the first concrete example of how gravity could emerge from quantum degrees of freedom that do not themselves contain gravity. It showed that geometry, curvature, and even black hole behavior could arise from entanglement and interactions among lower dimensional constituents. The holographic principle extends beyond this specific example, inspiring new ways of thinking about spacetime itself. If the geometry of a region is encoded on its boundary, then the area of surfaces becomes more fundamental than the volume they enclose. Distances and curvature may arise from patterns of entanglement, linking different degrees of freedom. In simplified models, tensor networks illustrate how entangled quantum systems can produce emergent geometries, with the structure of the network determining the shape of the effective space. These models do not claim to describe the universe exactly, but they reveal how concepts from quantum information can generate geometric features naturally, offering clues about how holography might operate in more realistic settings. One of the most remarkable insights arising from holographic reasoning is the relation between entanglement entropy and geometric area. The Ryu-Takayanagi formula states that in certain holographic systems, the entanglement entropy of a region in the boundary theory is given by the area of a minimal surface in the bulk gravitational theory. This relationship connects a purely quantum quantity, entanglement, with a geometric one, area. It suggests that the structure of spacetime may be encoded in how quantum information is shared and distributed. When entanglement changes, geometry changes. When correlations deepen or weaken, spacetime stretches or contracts. In this view, geometry is not elemental, it is woven from entanglement. The holographic principle reshapes our understanding of what it means for something to exist within a region of space. In ordinary physics, we imagine that every point inside a volume possesses its own independent degrees of freedom, and that the behavior of the whole system emerges from the dynamics of these local elements. Holography tells us that this picture may be incomplete. If the maximum information content of a region is determined by its boundary area, then the number of independent degrees of freedom inside the region cannot scale with volume. Instead, the interior description must be redundant in some way, with the essential information residing on the boundary. This reinterpretation is subtle, but it carries enormous weight. It suggests that much of what we perceive as spatial structure may be a projection of deeper informational relationships. This perspective also offers insight into the nature of black hole entropy. The area law, which stands as one of the strongest hints that spacetime may have a microscopic origin, fits naturally within the holographic framework. If the degrees of freedom that give rise to gravitational phenomena are associated with boundaries rather than interiors, then it makes sense that entropy scales with area. The holographic principle provides a coherent way to interpret this scaling, unifying black hole thermodynamics with quantum information in a broader conceptual structure. It transforms the horizon from a mere geometric surface into a locus of fundamental information, encoding the microstates that define the gravitational system. As researchers studied the implications of ADS-CFT more deeply, they uncovered surprising connections between entanglement and geometry. In the boundary theory, entanglement between different regions of the quantum system determines how the bulk geometry emerges. Increasing entanglement can bring distant points closer together, while diminishing entanglement can stretch them apart. This behavior corresponds to the way spacetime curves in response to energy and matter in general relativity. Although ADS-CFT describes a mathematical model rather than our universe, it demonstrates that gravitational dynamics can arise naturally from the properties of quantum information. The fact that entanglement patterns shape geometry so effectively suggests that something similar may occur in more realistic settings, even if the precise correspondence differs from ADS-CFT. Tensor network models provide a visual illustration of how such emergent geometries might arise. These networks consist of nodes connected by links, with each link representing quantum entanglement between degrees of freedom. When arranged in specific ways, the networks mimic the causal and geometric structure of the bulk spacetime in holographic theories. The simplicity of these models belies their power. They show that geometry does not need to be fundamental. It can arise from relational structures, from how information is shared and processed among underlying elements. These networks also help researchers explore how horizons, curvature, and even gravitational dynamics might emerge in systems far removed from traditional gravitational physics. The Ryu-Takayanagi formula strengthens this connection by providing a precise link between entanglement entropy and the geometry of minimal surfaces in the bulk. In certain holographic systems, the entanglement entropy of a region on the boundary equals the area of a surface in the bulk that spans the boundary of that region. This remarkable relationship does more than connect two mathematical quantities. It suggests that geometry itself is a bookkeeping device for entanglement. The area of a surface corresponds to how much information is shared across it. When entanglement patterns change, the geometry adjusts to reflect those changes. This picture echoes the deeper idea that spacetime may be emergent from quantum correlations rather than constructed from independent points in a pre-existing backdrop. These insights raise profound questions about the fundamental nature of reality. If spacetime can emerge from entanglement, then what does it mean for a location to exist? What does distance signify when it may simply reflect the strength of informational ties? These questions push the boundaries of physics into conceptual territory that once belonged only to philosophy, yet they are grounded in precise mathematical frameworks. The success of holographic dualities shows that these ideas are not idle speculation, but tools capable of explaining and predicting concrete physical phenomena. The lessons of the holographic principle extend far beyond the particular systems in which they were first discovered. They point toward a universe where geometry is not etched into the fabric of existence, but drawn from the flow of information. In this view, spacetime is not an independent arena, but an emergent tapestry woven from entanglement, correlations, and constraints on how information can be distributed. The area law for entropy becomes a clue to this deeper structure, telling us that horizons do not simply separate regions of space, but mark boundaries in the landscape of accessible information. The fact that the entropy of a region depends on its boundary area reveals that the interior degrees of freedom must be limited in a way that contradicts the naive picture of spacetime as a smooth continuum with independent data at every point. This shift in perspective becomes even more compelling when one considers how holography influences our understanding of energy, gravity, and the dynamics of spacetime itself. In holographic dualities, the motion of matter in the bulk corresponds to excitations in the boundary theory. Gravitational attraction maps to changes in entanglement structure. Even the simplest geometric features can be reinterpreted as consequences of informational patterns. Though our universe is not known to possess the same kind of boundary structure as the spaces described in ADS-CFT, the success of the correspondence demonstrates that the emergence of gravity from non-gravitational systems is possible. It proves, in a mathematically precise setting, that gravity can arise from something else entirely, something encoded in fewer dimensions. This revelation encourages a re-evaluation of the separation between geometry and quantum information. Entanglement, once seen as a quirky property of quantum mechanics, becomes a central ingredient in the architecture of spacetime. The more entangled a system is, the more tightly its geometry appears to be stitched together. When entanglement erodes, geometry frays. In certain models, severing entanglement can even cause spacetime to tear apart, hinting that the continuity of space depends on the persistence of informational relationships. Though these models are simplified, abstractions, they offer a window into the idea that geometry might not be fundamental but emergent from deeper mathematical structures. The holographic principle also informs our understanding of black holes in new ways. If the interior and exterior of a black hole are encoded holographically, then the information paradox may need to be reframed. The apparent loss of information inside a black hole may not represent a failure of quantum mechanics, but a failure of classical geometry to reveal how information is stored. In holographic theories, information is never lost because the boundary description captures the entire physical content of the system. The interior emerges only as a derived notion, dependent on entanglement among the underlying degrees of freedom. If a similar picture applies to real black holes, the flow of information through evaporation might be encoded in the structure of space-time itself in a way that resolves the paradox without violating quantum principles. At the same time, holography reveals the limitations of current ideas about emergent gravity. While it provides a compelling demonstration that gravity can arise from lower dimensional systems, it does not show that our universe operates holographically in the same way. The spaces used in ADS-CFT are highly idealized, possessing symmetries that the real universe does not appear to share. Moreover, holography does not eliminate the need for dark matter or dark energy, nor does it offer immediate solutions to cosmological puzzles. Yet its conceptual impact is undeniable. It demonstrates that gravity need not be fundamental and that thermodynamics, information, and geometry may be intertwined at the most basic level. Even if holography is not the exact blueprint of our universe, it has transformed the way physicists think about spacetime. It suggests that the fundamental ingredients of reality may not be points in space, but patterns of entanglement. That distances may measure how strongly two regions of a quantum system are correlated. That curvature may reflect informational constraints rather than geometric axioms. These insights resonate with the deepest questions of modern physics, and they prepare us to examine the challenges that remain for any entropic or emergent approach to gravity. The idea that gravity might emerge from entropy or from deeper informational structures captures the imagination because it offers a unifying way to view spacetime, thermodynamics, and quantum theory. Yet scientific beauty must always answer to empirical rigor, and it is here that entropic gravity faces its greatest tests. A theory may be elegant, intuitive, even philosophically appealing, but if it cannot reproduce the precision of observational data, it remains a hypothesis rather than a replacement for established physics. Entropic models illuminate what gravity could be, but they struggle when confronted with the full breadth of gravitational phenomena revealed by telescopes, satellites, and gravitational wave detectors. This tension between conceptual promise and empirical difficulty has shaped the scientific community's cautious stance toward emergent gravity. A major challenge arises from the absence of a concrete microscopic model underlying these proposals. The thermodynamic and informational analogies suggest that spacetime might emerge from deeper degrees of freedom, but no theory yet provides a detailed description of what those degrees of freedom are or how they behave. Without such a foundation, entropic gravity remains suspended between metaphor and mechanism. It suggests broad principles, but cannot specify the microscopic interactions needed to generate precise gravitational effects. In contrast, general relativity provides exact equations that match observations with extraordinary accuracy. Any alternative must equal or surpass this precision, and entropic models have not yet achieved that level of detail. Another difficulty lies in reproducing the full range of gravitational predictions across all regimes. General relativity has passed tests in weak fields, strong fields, and dynamic situations. It predicts gravitational waves, black hole mergers, and the intricate ways light bends around massive objects. These predictions have been confirmed repeatedly. Entropic gravity, however, struggles to reproduce strong field effects from first principles. The thermodynamic arguments that give rise to Newtonian gravity within these models do not easily generalize to scenarios involving extreme curvature or rapid motion. They do not provide a clear derivation of gravitational waves, and they do not naturally reproduce the rich phenomenology of black holes seen in observations and simulations. Cosmology presents an even more significant challenge. The large-scale structure of the universe, the distribution of galaxies, the temperature fluctuations in the cosmic microwave background, and the accelerated expansion of the cosmos all fit within a model that includes dark matter and dark energy. This model, known as the Standard Cosmological Model, matches observations across a staggering range of scales. Entropic alternatives, including Verlinde's extended framework, have not been able to match this success. While they can approximate certain galactic rotation curves, they cannot replicate gravitational lensing in galaxy clusters or the detailed statistical features of the cosmic microwave background. The standard model fits this data with extraordinary precision. Emergent gravity does not. Even when entropic gravity can mimic certain gravitational behaviors, it often does so by introducing assumptions that are not derived from underlying principles. These assumptions may appear reasonable, but without a microscopic justification, they lack the explanatory depth required of a fundamental theory. For example, the idea that entropy associated with matter distribution generates an additional gravitational component may seem appealing, but the precise nature of this entropy, how it forms, and how it evolves, remain unclear. Without answers to these questions, entropic gravity cannot compete with the predictive power of models that incorporate dark matter as a physical substance. Despite these limitations, the appeal of emergent gravity persists because it touches on some of the deepest unresolved questions in physics. It challenges researchers to consider whether spacetime is fundamental or emergent, whether gravity is a force or a thermodynamic consequence, and whether information might be the true substrate of physical law. These are profound possibilities, and they merit exploration. But the gap between conceptual attractiveness and empirical adequacy must be recognized. A theory cannot succeed solely because it is elegant. It must describe the universe more accurately than the theories it seeks to replace. The limits of entropic gravity become even more apparent when we consider the tremendous success of general relativity in describing gravitational phenomena across a wide range of contexts. The bending of starlight as it passes near massive bodies has been measured with exquisite precision. The time dilation experienced by clocks in different gravitational fields has been verified by satellites orbiting the Earth. The inspirals and mergers of distant compact objects produce gravitational waves whose waveforms match detailed numerical predictions drawn directly from Einstein's equations. These triumphs do more than validate a mathematical framework. They illuminate the extraordinary accuracy with which general relativity captures the behavior of spacetime itself. Any alternative theory must account for all of these successes while also explaining the puzzles that remain. Entropic models face difficulty in this regard because they offer broad thermodynamic analogies, but lack the fine-grained structure needed to make precise predictions. Thermodynamic reasoning can recover Newtonian gravity under certain assumptions, but achieving the full dynamical richness of general relativity requires a level of detail that entropic approaches have not yet supplied. The Einstein equation contains intricate relationships between curvature, matter, and energy flow that cannot be derived from simple entropy gradients alone. To reproduce these relationships, an entropic theory would need to identify the microscopic degrees of freedom that generate geometry and specify how their statistical behavior produces the tensor structure of Einstein's equation. Without this microscopic underpinning, entropic gravity risks becoming too vague to challenge an established framework that is empirically robust. Strong field environments reveal these shortcomings starkly. Near black holes, where spacetime curves sharply and gravitational effects become extreme, general relativity has proven remarkably accurate. The shadows of black holes imaged by horizon-scale telescopes match predictions with striking fidelity. The ring-down signals observed after black hole mergers conform to the precise oscillation patterns expected from Einstein's equations. Entropic approaches, by contrast, do not yet offer a way to derive these strong field signatures. While the thermodynamic nature of horizons offers inspiration, it does not provide the detailed mathematical machinery required to match observations. Without such machinery, entropic gravity remains a conceptual framework rather than a predictive theory. Cosmology further deepens the challenge. Observations of the cosmic microwave background show tiny variations in temperature that encode the initial conditions of the universe. These variations have been mapped with extraordinary precision by multiple satellites, and the patterns they reveal align closely with predictions from models that include dark matter. The formation of galaxies, the growth of large-scale structure, and the distribution of matter across cosmic filaments all arise naturally within this framework. The inclusion of dark matter allows gravity to amplify small fluctuations into the cosmic web observed today. Entropic gravity, lacking a concrete mechanism to generate the same effects, cannot reproduce this sequence of cosmic history. Even when entropic theories attempt to account for cosmological behavior, they often struggle with lensing. Gravitational lensing occurs when massive objects bend the paths of light traveling near them. Galaxy clusters bend light far more strongly than their luminous matter suggests. Dark matter explains this easily by adding unseen mass. Entropic gravity must instead modify the way geometry responds to matter, but doing so in a way that matches the observed lensing signals remains difficult. The precision with which lensing has been measured in recent years leaves little room for approximate explanations. The bending of light traces the curvature of spacetime directly. Any theory that aspires to replace or refine general relativity must match this curvature across a vast range of scales. Despite these empirical gaps, the scientific appeal of entropic gravity endures because it invites researchers to explore alternative routes toward unification. It demonstrates that gravity may not be as fundamental as once believed, and that information and thermodynamics might play deeper roles in shaping spacetime. Even if entropic gravity does not describe the true nature of gravity, the questions it raises have pushed the field forward. They have inspired new connections between quantum information science and gravitational physics, leading to advances in the study of entanglement, holography, and the emergence of spacetime from non-gravitational systems. The most significant obstacle facing entropic approaches is the lack of definitive evidence in their favor. Ideas rooted in thermodynamics and information theory offer promising conceptual frameworks, but without clear observational signatures, they cannot rise to the level of established physics. General relativity succeeded not only because of its mathematical beauty, but because it made precise predictions that could be tested. It anticipated the bending of light by stars, the precession of Mercury's orbit, the slowing of clocks in gravitational fields, and the expansion of the universe. Later, it predicted gravitational waves, and detectors eventually heard the faint murmurs of colliding black holes across billions of years of cosmic time. Entropic gravity has not yet offered predictions of this caliber. It provides a language for thinking about gravity, but it does not yet provide the quantitative tools required to rule out or confirm its claims. Another difficulty arises from the nature of emergent phenomena. When a macroscopic behavior emerges from microscopic interactions, the process typically smooths over details that vary from system to system. The speed of sound in air depends on temperature and the molecular mass of the gas, but the equations governing sound waves do not reveal the identities of the molecules themselves. Similarly, if gravity truly emerges from microscopic degrees of freedom, then the Einstein equation may describe an average behavior rather than a precise revelation of the underlying physics. This raises a challenge for entropic models. Unless they specify the microstates from which gravity emerges, they cannot predict how gravity might deviate from Einstein's description at small scales or high energies. Without these predictions, the theories remain incomplete. This incompleteness stands in contrast to other approaches to quantum gravity, such as string theory and loop quantum gravity, both of which attempt to identify the microscopic ingredients of spacetime. Even if those approaches remain speculative, they at least propose explicit structures. Entropic gravity, by comparison, offers a broader conceptual vision, but without identifying the specific building blocks required to implement it. As a result, it cannot yet tell us how spacetime behaves near singularities, how information escapes from evaporating black holes, or how geometry evolves at the smallest scales. These are among the most pressing questions in modern physics, and any theory that hopes to explain gravity at a fundamental level must eventually grapple with them. Furthermore, the hints connecting entropy, information, and geometry may point toward a deeper truth that is not captured fully by entropic gravity. The appearance of entropy at horizons, the thermal nature of accelerating frames, and the holographic structure of certain gravitational systems all suggest that thermodynamics is intertwined with spacetime. But this intertwining may reflect the structure of quantum gravity rather than a literal emergence of gravity from entropic forces. In other words, the relationship between entropy and gravity may be symptomatic rather than causal. Gravity may not arise from entropy. Instead, entropy and gravity may both arise from a deeper microphysical framework that has not yet been discovered. The scientific community's consensus reflects this distinction. Researchers appreciate the insights emerging from entropic reasoning, but they also recognize the limitations and uncertainties. The prevailing view is that while entropic ideas are intriguing and valuable, they do not yet constitute an alternative to general relativity or the dark matter paradigm. They are signposts along the path to a deeper theory, not the destination. They challenge scientists to think creatively, but they do not yet provide the empirical reliability required to reshape our understanding of the cosmos. Even so, the questions raised by entropic gravity continue to guide the search for new ideas. What is the microscopic structure of spacetime? Why does the universe obey an area law for entropy? How does entanglement shape geometry? These questions remain unresolved, and the pursuit of their answers drives theoretical physics toward new and unexplored territories. Whether or not gravity is emergent, the exploration of entropic ideas has illuminated connections between thermodynamics, quantum theory, and geometry that will likely play a central role in the ultimate theory of nature. The search for a deeper understanding of gravity has led physicists down many paths, each guided by different assumptions about what spacetime is made of and how the universe behaves at its smallest scales. While entropic gravity offers one possible lens, other approaches attempt to construct gravity from quantum principles more directly. These frameworks differ greatly in method and interpretation, yet they share a surprising set of recurring themes. Entanglement, discreteness, thermodynamics, and the flow of information appear again and again, as if the universe keeps whispering the same clues through multiple mathematical languages. Even when these theories diverge in their predictions, the patterns they reveal provide insights into what the microscopic origin of spacetime might be. One of the earliest and most thoroughly developed attempts to quantize gravity is loop quantum gravity, which begins by questioning whether spacetime is continuous or granular at the smallest scales. In this framework, space is not a smooth geometric fabric, but a network composed of discrete units of area and volume. These units arise from the quantization of geometric operators, much as energy levels in an atom emerge from the quantization of the electromagnetic field. The loops and nodes that make up these networks form a kind of quantum scaffolding from which classical spacetime emerges when viewed at scales much larger than the spacing between the discrete elements. This approach replaces the continuity of spacetime with a lattice-like structure, though the lattice is not fixed in place but evolves dynamically according to quantum rules. Loop quantum gravity offers intriguing hints about how singularities might be resolved. In classical general relativity, the centers of black holes and the origin of the universe contain singularities where curvature becomes infinite and the equations break down. In loop quantum gravity, however, the discreteness of spacetime prevents the formation of such infinities. The geometry cannot shrink below a minimum size, and the evolution of the system can continue through regions where the classical theory would fail. This raises the possibility that singularities may be replaced by bridges or transitions into new phases of spacetime. Although the full implications of these ideas remain uncertain, they demonstrate how quantized geometry can provide answers where classical geometry falters. Another major approach to quantum gravity arises from string theory, which proposes that the fundamental building blocks of nature are not point particles, but extended one-dimensional objects whose vibrational modes determine the properties of particles and forces. In this framework, spacetime itself can be emergent, arising from the collective behavior of strings and higher dimensional objects known as branes. Remarkably, string theory was the first framework to calculate the microscopic origin of black hole entropy for certain highly symmetric black holes, showing that the number of quantum states associated with the black hole matched the entropy predicted by the area law. This achievement revealed that geometric entropy could emerge from quantum microstates and provided strong evidence that the relationship between gravity and thermodynamics has a deeper origin. String theory also gives rise to the holographic principle in a natural way. The correspondence between gravitational systems and lower dimensional quantum theories emerged from the mathematical structure of string theory, reinforcing the idea that gravity can arise from non-gravitational degrees of freedom. In this sense, string theory and holography do not merely coexist. They intertwine. They demonstrate that space-time geometry, gravitational dynamics, and quantum information may be facets of a single underlying system. Even though string theory operates in higher dimensional spaces and requires assumptions that remain unproven, the coherence of the framework has made it one of the leading candidates for a theory of quantum gravity. Beyond string theory and loop quantum gravity lies another class of ideas that approach spacetime from an entirely different angle. Causal set theory begins with the premise that the fabric of the universe is not a continuous manifold, but a collection of discrete events connected by causal relationships. In this framework, spacetime is fundamentally a network of points ordered by cause and effect, with geometry emerging from the number and arrangement of these relationships. If two events are linked in a causal way, then one influences the other. If they are not, then they belong to different branches of the evolving structure. This picture of spacetime resembles a growing tree of events rather than a smooth surface, and it suggests that the continuity we perceive may arise only when enormous numbers of discrete causal links are examined collectively. The appeal of causal set theory lies in its simplicity. Instead of assuming spacetime geometry and then quantizing it, the theory builds spacetime from the ground up by defining the most primitive relationships between events. Distances, angles, and curvature appear not as fundamental quantities, but as emergent properties of the network. This approach aligns naturally with the thermodynamic and informational perspectives explored in earlier chapters. If spacetime emerges from the connections between events, then entropy and information must play central roles in determining how these connections evolve. Horizons, for example, could arise when large portions of the causal network become inaccessible, and entropy could reflect the number of possible causal configurations compatible with a given large-scale structure. Despite their differences, these quantum gravity programs share a common theme. They all point toward a universe where geometry is not the starting point, but the result of something deeper. In loop quantum gravity, geometry emerges from discrete quantum states. In string theory, geometry arises from the vibrational patterns and interactions of extended objects. In causal set theory, geometry grows from networks of cause and effect. And in holography, geometry is a reflection of entanglement. This repeated appearance of emergence is striking. It suggests that gravity may indeed be a collective phenomenon, not a fundamental force, but a macroscopic consequence of microscopic processes we have only begun to understand. Another shared pattern involves the role of entanglement. In nearly every modern attempt to unify gravity and quantum mechanics, entanglement appears as a central ingredient. It shapes geometry in holographic theories. It influences the structure of quantum fields. It determines the entropy associated with horizons. It even plays a role in approaches that appear purely geometric at first glance. Entanglement seems to be woven into the very essence of spacetime, acting as the thread from which distances and relationships are derived. This has led many researchers to suspect that information, not matter or energy, may be the true foundation of physical law. Thermodynamic analogies also recur across these frameworks. The equations governing black hole horizons resemble the laws of thermodynamics. The Einstein equation can be rewritten as a thermodynamic relation, connecting entropy and energy flow. Holographic dualities link entanglement entropy with geometric area. Even in approaches with no explicit thermodynamic assumptions, the behavior of spacetime near horizons reveals patterns reminiscent of heat and temperature. This convergence suggests that the relationship between gravity and thermodynamics is not accidental, but fundamental. While entropic gravity attempts to make entropy the direct cause of gravitational attraction, the broader picture emerging from quantum gravity research is more nuanced. Thermodynamics may not cause gravity in a literal sense, but both may arise from the same underlying microstructure. These shared clues provide guidance even when the theories themselves diverge. They hint that the universe may be organized according to principles that transcend any one mathematical framework. Information appears fundamental. Entanglement appears essential. Geometry appears emergent. Whether these themes reflect the true structure of reality or simply the limitations of current knowledge remains an open question, but their persistence across multiple independent lines of investigation is difficult to ignore. As these diverse approaches to quantum gravity unfold, they reveal a landscape that is far from unified, yet rich with recurring patterns. Each framework begins from different assumptions about what spacetime is made of, but they converge on certain ideas as if guided by an unseen compass. Chief among these is the notion that spacetime, and therefore gravity, may not be fundamental. Instead, both may arise from deeper building blocks that do not resemble geometry at all. The smooth continuum described by general relativity could be a large-scale approximation, similar to how a calm ocean's surface conceals the chaotic motion of countless water molecules beneath. From a distance, the ocean appears continuous, but up close, it reveals a world of fluctuations and interactions. Spacetime may be no different. When researchers examine these theories, they often find that the ingredients responsible for the emergence of geometry behave according to principles that mirror thermodynamics. The idea that spacetime has temperature, that horizons possess entropy, and that gravitational equations can be written as thermodynamic relations suggests that the universe may be governed by statistical laws at its deepest levels. These laws would not be expressed in terms of spacetime dynamics directly, but in terms of how countless microscopic degrees of freedom organize themselves. The familiar geometry of the universe would then emerge in much the same way that pressure, temperature, and density emerge from the collective behavior of molecules in a gas. This viewpoint transforms the meaning of gravity. Instead of being a force transmitted across space, it becomes a reflection of how information is arranged and how entanglement patterns shift when energy moves from one region to another. The curvature of spacetime would then be a macroscopic trace of microscopic processes that bind the universe together. Such a transformation mirrors the shift that occurred in the 19th century, when scientists realized that heat was not a substance, but a measure of motion. In a similar way, gravity may not be a fundamental interaction, but an expression of deeper informational and statistical laws. Even the difficulties encountered by current theories reinforce this perspective. The fact that no single quantum gravity program has succeeded in providing a complete description of nature suggests that our understanding remains incomplete. Yet the recurring appearance of certain concepts across these programs reveals that they are circling around common truths. Entanglement appears again and again as the stitching that binds spacetime. Thermodynamics appears as the language through which spacetime communicates. Discreteness appears as a sign that space may not extend smoothly to infinitely small scales. Each theory shines a light on part of the puzzle, and although none has illuminated the entire picture, together they outline the contours of a deeper reality. This deeper reality may not resemble anything familiar. It may not be geometric. It may not be continuous. It may not even be spatial in the conventional sense. Instead, it may consist of a network of relationships, a matrix of information, or a tapestry of quantum correlations from which spacetime emerges as a useful approximation. The challenge for physics is to identify these building blocks and understand how their interactions give rise to the universe we observe. If successful, this effort would not only reconcile general relativity with quantum mechanics, but also provide answers to questions that have lingered for decades, such as the origin of black hole entropy, the nature of singularities, and the fate of information in gravitational systems. For now, the field remains in a state of exploration. Each theory offers possibilities but also raises new questions. Entropic gravity, holography, loop quantum gravity, string theory, and causal set theory all point toward the same mystery from different angles, like explorers circling a mountain whose summit remains hidden in cloud. The convergence of their insights suggests that the mountain is real, even if no one has yet reached the peak. As research continues, the shared clues drawn from these competing ideas may guide future discoveries, revealing the microscopic architecture that underlies the geometry of the universe. Our understanding of gravity rests on a delicate balance between certainty and mystery. On one side stand the truths etched firmly into observation. On the other lies a landscape of unanswered questions shaped by thermodynamics, quantum information, and the search for the microscopic origin of spacetime. Between these extremes lives the gravitational world we encounter each day, a world where Einstein's equation maps the curvature of spacetime with extraordinary precision. Yet beneath this precision lies a chorus of clues whispering that geometry might not be the final story. Black hole horizons carry entropy that scales with area instead of volume. Accelerated observers feel warmth where inertial observers feel vacuum. Entanglement appears wherever geometry emerges. These facts create a tension that modern physics has not resolved. One of the strongest pillars of our knowledge is the thermodynamic behavior of black holes. Horizons possess entropy, and that entropy follows the area law with remarkable consistency. Hawking radiation emerges as a real physical consequence of quantum fields in curved spacetime. Even if the radiation is too faint to observe directly for astrophysical black holes, the theoretical foundation underlying it is stable and deeply intertwined with the structure of quantum theory. No complete theory of gravity can ignore these thermodynamic lessons. Horizons encode information, geometry carries entropy, temperature emerges from curvature. These facts transform black holes from mere endpoints of collapse into laboratories for fundamental physics. Equally firm is the observational success of general relativity, the bending of starlight, the slowing of time near massive bodies, the expansion of the universe, the detection of gravitational waves from distant mergers, and the shimmering silhouettes of supermassive black holes all align with Einstein's description of spacetime. The theory has succeeded not only in gentle gravitational fields, but in violent cosmic collisions where spacetime twists and rings like a struck bell. Any emergent theory of gravity must reproduce this precision in every measurable regime, for the universe does not bend to speculation. It bends to curvature, and curvature follows the Einstein equation with unwavering fidelity. Yet for all its triumphs, general relativity leaves questions untouched. It does not explain what happens to information inside evaporating black holes, or what constitutes the microstates, whose count yields horizon entropy. It does not reveal the quantum origin of spacetime or the structure that prevents infinite curvature at singularities. It predicts its own breakdown at the very scales where quantum theory becomes unavoidable. In this way, relativity contains its own boundary. Its successes illuminate where it works. Its gaps reveal where deeper principles must lie. The area law for entropy, the holographic nature of horizon physics, and the role of entanglement in shaping geometry point toward those deeper principles even as the full picture remains hidden. The universe also speaks through cosmology. The cosmic microwave background shows subtle variations in temperature that encode the seeds of galaxies. These patterns match a universe in which dark matter shapes the large-scale distribution of structure. Galaxy clusters exhibit gravitational lensing far stronger than can be explained by luminous matter alone. The cosmic web, stretching across billions of light-years, forms naturally when dark matter amplifies tiny fluctuations in the early universe. Entropic gravity cannot yet replicate this observational power. Its conceptual elegance does not overcome the precision with which the standard cosmological model matches the data. Though dark matter remains undetected in laboratories, its gravitational influence is written across the cosmos with convincing clarity. Even so, the possibility that gravity is emergent continues to guide the questions physicists ask. If entropy and geometry are linked so intimately, what microstructure gives rise to this connection? If entanglement shapes spacetime, what deeper quantum system produces those correlations? If holography hints at a lower dimensional blueprint of the universe, what does it imply about the nature of reality? These questions push beyond what we know into the territory of what we do not yet understand. They remind us that certainty is not the end of inquiry, but its beginning. In the end, what the universe reveals is not contradiction, but invitation. Gravity works with astonishing precision, yet its foundations may lie in information rather than geometry. Black holes obey thermodynamic laws, yet their microstates remain hidden. Cosmology fits the dark matter model, yet the nature of dark matter eludes detection. The known and the unknown coexist, forming a frontier shaped by measurement, guided by theory, and sustained by curiosity. Gravity may be fundamental, or it may be emergent, but the search for its origin continues because the universe continues to offer hints that the story is not finished. At the edges of current knowledge lies a question that has become the guiding star for modern physics. What is spacetime made of? The geometry described by general relativity has shaped our understanding of the universe for over 1 century. Yet evidence from thermodynamics, holography, and quantum gravity suggests that this geometry may not be fundamental. Instead, it may arise from deeper microscopic ingredients that have not yet been seen. Ingredients that shape entropy, entanglement, and information long before they shape curvature. The pursuit of this hidden structure defines the frontier of gravitational research, a frontier where observation and imagination move in parallel. New instruments have transformed the search for answers. Observations of distant galaxies by space telescopes reveal how cosmic structure evolves across billions of years. Maps of dark matter, drawn from gravitational lensing, show the invisible scaffolding that shapes the universe. Black hole images reveal shadows and glowing rings formed by light orbiting near horizons. Gravitational wave detectors hear the tremors of spacetime itself as massive bodies collide. Each of these observations pushes general relativity into regimes where new physics might appear, searching for small deviations that could reveal the microstructure beneath geometry. At the same time, theoretical work explores how spacetime might emerge from quantum ingredients. Some approaches imagine a universe built from discrete units of area and volume, with geometry arising only when enormous numbers of these units cooperate. Others envision spacetime as a web of entanglement in which distance is measured not by rulers, but by the strength of quantum correlations. Still others treat spacetime as a holographic projection, encoded on surfaces that store the fundamental information of the universe. Though these pictures differ, they converge on one idea. Geometry is not primary. It is secondary, a large-scale appearance created by something deeper.